Hey class, in today's lesson we're going to talk about solving exponential and logarithmic equations, which is found in section 3.4 part 2. Our objectives are to solve logarithmic equations, to use exponential and logarithmic equations, and to model and solve real-life problems. In our first problem, we have log base 3 of 5x minus 1 equal to log base 3 of x plus 7. So essentially what we're supposed to do here is we're supposed to solve log equations. So the last chapter was more so the last section was more so solving exponential equations, but this one is solely based on log equations. So what you should notice is that our logs are equal, our log bases are the same. So if our log bases are the same, then what is left over is actually the same as well. So what we have then is 5x minus 1 equal to x plus 7. This then just becomes a multi-step equation. So if I subtract x and add 1, I'm left with 4x equal to 8. If I divide by 4, x will then equal 2, and x is our answer. All right. On the second one, again, when we have log, the goal is to have just a single log. So we're going to have to divide by 2 on the first one. That's going to give me log base 5 of 3x equal to 2. And then what we want to do is we want to change that into exponential form because that's going to be the best way to solve. So remember, if log is bay, then to write that in exponential form, we're going to have 5 squared equals 3x. That's essentially 25 equal to 3x. If I divide by 3, x will then equal 25 thirds, which is about 8.3 repeating. Let's try some more examples. All right, so I have the natural log of x equal to 2. What I would do, just so that we can get a better context of this, is that I would rewrite the natural log of 2 as log, or the natural log of x, I would rewrite as log base e of x equal to 2. All right, if I change that to exponential, then that becomes e squared equal to x. And that I can put into my calculator, and I would get x as about 7.39. All right, again, on the second one, I just want a single log. If I can get a single log, then I can switch it to exponential, and then we'll be fine. So switching colors just for the context of being able to see. If I subtract 5, If I subtract 5 on both sides, I'm left with 2 times the natural log of x equal to negative 1. Then I need to divide by 2, and I would get that the natural log of x is equal to negative 1/2. Again, I want to rewrite natural log of x as log base e of x. So this is really log base e of x equals negative 1/2. All right, if I write that in exponential form, that's 1/2, sorry, we would get e to the negative 1/2 equals x. And that, again, we can type into our calculator, and we would get that x is about 0.61. All right, let's take a look at example 5. All right, with example 5, we're going to solve for x in the equation that the natural log of x minus 2 plus the natural log of 2x minus 3 equals 2 times the natural log of x. All right, so if we follow our properties, you will remember that addition really means to multiply. Right? It really means to multiply. So what we're left with is really the natural log of x minus 2 times 2x minus 3. And that still equals, and by the way, this here, because there's a number in the front, that's really a power. So that's really the natural log of x squared. Okay, if we go ahead and simplify this center, these two binomials, what we'll get is that the natural log of 2x squared minus 7x plus 6 equals the natural log of x squared. All right, since each side is equal to natural log, they've essentially kind of canceled one another out, and we're left with 2x squared minus 7x plus 6 equal to x squared. All right, if we can set this equal to 0, this will then become just a quadratic equation. So if I subtract x squared on both sides, I am left with x squared minus 7x plus 6 equal to 0. Now, we know that if we do AC, the two factors that we will get that multiply to get 6 but add up to give you negative 7 are x minus 1 and x minus 6. Thus, our x values will be x equal to 1 and x equal to 6. But the one thing that I will say with this problem, because this, and it actually even points out for us to check for extraneous solutions, is that these two values, though they may seem that they are both answers, they both may not be answers. So what we should do is we should substitute both of these answers back in. So for example, if I tried to substitute 1 back into this equation, that means that I would have the natural log of 1 minus 2, which is negative 1, plus the natural log of 2 times 1 is 2, and then 2 minus 3 is also negative 1, equal to 2 times the natural log of 1. If we remember, guys, it is not possible to have a natural log of a negative number, and it's because no base raised to any power will ever give you a negative number. So essentially, because of these two pieces here, x equals 1 is not possible. So x equals 1 is actually called an extraneous solution. It seems like it's real, but it's not, okay? And by the way, if you substitute x equals 6 back in, it would work out just fine. So x equals 6 is our only real solution. Let's take a look at our last problem, or close to last problem. All right, let's approximate the solution of the natural log of x equal to x squared minus 2. All right, so essentially what we have is, it'd be easier and actually a little bit better if we moved everything to one side, because if we're trying to approximate a solution, I'm going to tell you now, it's best if we do that on a graphing calculator. So if I subtract x squared and add 2 to both sides, that's going to leave me with negative x squared plus 2 plus the natural log of x equal to 0. So what's best for us is for us to graph this in our graphing calculators. And specifically what I mean is we're going to graph y equals negative x squared plus 2 plus the natural log of x. And essentially what you're going to do is you're going to get some graph, and your job is to find the zeros. And remember, zeros are actually your x-intercepts, so where it crosses the x-axis. And what we'll get for values of x is about 0.14 and x is about 1.56. All right, now we're on our last problem. All right, so in example 7, it says you have deposited $500 in an account that pays 6.75% interest compounded continuously. How long does it take your money to double? So what we're going to want to do is, first of all, the fact that it says compounded continuously lets us know that we're going to use the formula A equals P times E to the RT power. All right, so if that's the case, P is our principal amount, and P is $500. E is still E. Our rate is 6.75%. But remember, what we do is we knock off the percent and move the decimal 2 places to the left. So that becomes 0.0675. So this is 0.0675 times the time. Well, that's what we're trying to figure out. We're trying to figure out how long it takes to double our money. Now, to double our money, if the initial investment was $500, then what we're hoping to have is 1,000, and A is the outcome, so 1,000 is what we will place here. All right, so that's all that the problem was telling us. Now it's our job to be able to find T. So to find T, what we're going to have to do is to make this just a single exponential function. So that means we're going to need to divide by 500. That's going to leave us with 2 equal to E to the 0.0675 T power. All right, remember, to get rid of E on both sides of our function, we're going to have to do the natural log. Okay, natural log and e will eliminate one another, and that will be left as the natural log of 2 equals 0.0675 t. Okay, finally, to get t, we will divide by 0.0675. So t is going to be about, if you type that into your calculator, you're going to get t is about 10.27 years. So it's going to take about 10.27 years for that person to double their investment at 6.75% interest. Guys, we are done. Remember, if you have any questions, please be sure to come see me for tutoring.